Alright, silly people, here's the situation. This time we're going to be numerically finding the Lagrange point for a satellite in orbit around the Earth. And again, the theory is kind of explained here. It's just a point in between the Earth and the Moon where the satellite is affected by both gravities of both bodies, but also it's always staying in between in the same spot, basically, as the moon orbits the Earth. So the first bit of the problem is actually to get this equation from basic principles. And it says assume circular orbits and assume that the Earth is much more massive than either the moon or the satellite, which I don't know why it says to assume that, because if you just, like, say, use the Newtonian gravitational force of the satellite on the Earth minus the Newtonian gravitational force of the satellite on the moon, that will be equal to the centripetal force of the satellite in motion, right? So plugging in all of those things there, you end up with the mass of the satellite canceling out because all of these terms depend on the mass of the satellite. And then you use the fact that angular velocity is just given by the linear velocity divided by the radius. And so you get the equation, which I went ahead and put 0 on the right-hand side so we can do the next bit of the problem, which is actually getting a value for it via Newton's method. So that should be pretty easy to do, actually. We can go ahead and put in all of these constants that the problem has stated there. So we've got G equals 6.674 E minus 11, M equals 5.974 E 24, M equals 7.348 E 22, and then R was 3.844 E8, and omega was 2.662 E minus 6. Right, so this is Newton's method. You just define a function, which I'm going to call L for reasons. It's going to be a function of R, and it's going to return this equation here with 0 on the right-hand side. So it's returning G star M over, in parentheses, R squared minus G star little m divided by, in parentheses, R minus R squared minus, in parentheses, omega squared times R, right? For Newton's method, you also happen to need the derivative of the function you're trying to solve. So that is still easy to do. We can just get an analytic derivative for that. So it's going to be G, or actually, now it's minus G, and actually minus 2 times G times M over R to the third, minus 2 times D times M over, in parentheses again, R minus R cubed, just a little bit of a chain rule followed up by quotient rule sort of thing. It's pretty uncomplicated. And then this is going to be just omega squared at that point, right? So you can do now your function which does Newton's method. It's going to have the same structure as before, except this time, Newman wants us to get to 4 significant figures, at least 4 significant figures accuracy. So that's where we're going to set our accuracy to 1e minus 4. The error is, as always, I'm going to set it to a really large number, and then while the absolute value of the error is greater than the accuracy, you just, first of all, calculate the error, which is now the function called at r divided by the function divided by the derivative of the function called at r. And then you take your guess and you subtract off that much error. And once it's through that loop, you have it return the value after it's been run through a few times. I think a good value to start with is 3 times 10 to the 8 meters away from the Earth. It's a pretty good guess, and when you run it, you get something that's like, oh snap. Well, I need to actually run the thing, so print Newton of 388. Just a little brain flatulence there. But yeah, it returns 3.26 times 10 to the 8 meters away from the Earth, which is the actual solution for L1. So I think we did pretty okay. All right.